that makes it easy for scientists and developers to experiment with quantum computing. So let me unpack what this means. So first of all, it's publicly accessible. Anyone can access Amazon Braket by just signing up for an AWS account, and it's accessible everywhere around the world as long as you have an account and a web browser. When we say Amazon Braket is fully managed, we mean that Amazon Braket comes with a software suite that allows you to do anything you might want with quantum computing, and we do all the heavy lifting for the infrastructure and code behind the scenes. So we're trying to make the process as easy as possible. It's on demand, and so it's a pay-as-you-go service. There are no upfront commitments, and also since this is a full-fledged Amazon Web Services service, you can expect all the other features of AWS, such as security, logging, monitoring, and so on, and integration with other services to be available or also apply to Amazon Braket. So we have 3 pillars in Amazon Braket. First, so these are build, test, and run. So first, build. To help you build your code, we provide a fully managed development environment based on Jupyter notebooks that comes pre-installed with including our own Amazon Braket SDK and also the Penny Lane library for quantum differential programming, as you've seen many times today already. So if you'd like to work locally and not on the web, that's also fine. All of this software you can also just download and run your local machine by using pip install, for example. Once these software environments, the Amazon Braket SDK, are meant to be hardware agnostic, so it should be easy to switch back and forth between testing locally to testing on the cloud to testing on quantum hardware. Once you build your code, you want to test it on something. So Amazon Braket provides high-performing circuit simulators, which we'll take a look at in a sec. Once you've tested the code on simulators, you want to run it on actual quantum hardware, and then you can just access these quantum hardware through Amazon Braket. You don't need to access individual. You don't need to try to individually access each quantum computer. You don't need to check the API for them individually. All this Amazon Braket gives you a unified experience to do all of this. So let's take a look at what this experience means. This is a screenshot of a managed notebook, but instead of showing this, let me just switch over to my browser. So over here, I'm at the AWS Management Console. I've already created a new account for this, and I've already onboarded to Amazon Braket. So if you take a look at the Amazon Braket console, this page shows you the devices and simulators available. I'll come back to this page later. Let me just show the notebooks over here. So you can create your own notebook instance, and this just runs a hosted Jupyter notebook instance on Amazon Braket. You can specify how much computing power you want. This will probably take 5 minutes, so let me just skip this and go straight to the notebook instance I've already created. So in here, we have a few example notebooks. This is also available in the GitHub repo if you'd like, but let's just take a look, getting started, and open one of these up. This is just a standard Jupyter notebook that you may know and love already, and you can run it as usual, but this also comes installed with the Amazon Braket SDK. So over here, for example, you can just run this example notebook. If you'd like to run it locally instead, you can just Google Amazon Braket, say dev guide. In the documentation over here, there's a link to the Braket Python SDK, and then you can just install the Amazon Braket SDK locally, and you can do the same thing on your machine. So let me switch back. Once you've built your code, you want to test it. So Amazon Braket comes with 3 simulators. There's the local simulator that comes packaged with the Amazon Braket SDK. You can run it on the local machine or on a notebook instance that you have on the Amazon Braket console. Or if you install it locally, then it just runs locally. this isn't hosted on the cloud. It's just run locally, so it's free. It doesn't need to talk to AWS. And because of that, this is the fastest option we have for, say, fewer than 20 qubits, because you don't have to worry about internet latency when communicating back and forth. Finally, next we have two managed simulators on AWS. So we have the state vector simulator, or SV1. This works by tracking the full state vector as it evolves through the quantum circuit. So if you have an n-qubit circuit, this keeps track of all 2 to the n quantum amplitudes. So that's 2 to the n complex numbers. This will take exponential time, but fortunately our simulator is very, very optimized. And so this gets you up to 34 qubits, which is much more than what you can do on the local simulator. And it's much faster for larger qubit sizes as well. And if you want to run multiple of these circuits at the same time, you can parallelize running multiple circuits on AWS. Sometimes, though, you have more specialized circuits, and for them, you can use the Tensor Network Simulator, or TN1. TN1 is not a general purpose circuit simulator. It doesn't work for all circuits. It's most useful for circuits that generate little entanglement, so sparse circuits or local circuits, or sometimes circuits with special structure. You can also use TN1. And for example, the quantum Fourier transform is an example. When you have a circuit that's like that, this simulator can get you up to 50 qubits. Finally, once you've simulated your code, you want to run it on an actual quantum computer. So Amazon Braket allows you to access quantum computers from 3 different companies. We have 2 quantum annealers from D-Wave, and for gate-based quantum computers, we have IonQ's trapped ion computer, and also Rigetti's Aspen 9 chip based on superconducting technology. Let's just go back to the earlier page, to the devices page. Over here, if you check devices, this just lists all the devices available on Amazon Braket, as well as when they're next available. So each device is available at some parts of the day. For example, if you take a look at Rigetti, you see that this is available in about 18 hours. It's available every day within these hours. And then there's some other information, for example, the cost and the number of qubits and the qubit topology. We've also mentioned the simulators earlier. You have similar information about the simulators down here on the devices page as well. And right now, we have these quantum computers available. You can expect in the fullness of time, it's our goal to bring all the other quantum technologies that are out there to Amazon Braket, and you can look forward to seeing more quantum computers accessible in the future. So we'll just do a simple example. This is just a basic JTZ circuit. So this just creates the equal superposition of the all 0 state and all 1 state. And so when you measure in the computational basis, you expect to get measurement results that are all zeros with 50% probability and all ones with 50% probability. Again, I'll just switch back to the console for this. So this is based on this example notebook in the Getting Started folder. One second, technical difficulties. Okay, here we go. So this is just some inputs. I'll get back to what this means in a sec. So our goal is just to build a JTZ circuit. So we start by instantiating a circuit object, add a Hadamard gate on the first qubit, and then apply a series of CNOT gates, as shown in this circuit diagram. And this is just a function to build this. So we specify that we want 10 qubits. And once we run this, this says that JTZ is a circuit on 10 qubits. And with above structure, if you just print it, this looks exactly like the circuit diagram we had earlier. Okay, now that we've built this circuit, we want to run it. So let's start. We always want to start with a local simulator. So you create a device by initializing a local simulator, and then you just say device.run, feed it the circuit you want, and then tell it the number of shots you want. So the number of shots is just the number of times you want to make a measurement on the final state. If you set to 0, then everything will be exact instead. Let's just do this. And this says that we get the all1 string 520 times and all0 string 480 times, which is roughly what you expect. It's roughly 50-50. And you can plot the results using standard plotting tools. That's using the local simulator. What if I want to run this on SV1? So if I scroll down a bit, the first thing I need to do is to specify the Amazon is to specify the location where I want my results to be stored. So if I go to the AWS console and I search for S3 over here, this is Amazon's storage service. During onboarding, I will have created a bucket, a storage location, just for Amazon Braket. So let me copy and paste this, put it over here. And then I'll just define a folder name where I want to store my results. Let's say QHack demo. And let's just run this. And then to initialize the device, I need to feed in a resource identifier. So this you can find also just by looking at the console. Over here, SV1, and copy and pasting this. So that's the same thing over here. You can run this. Let's run it on a 15-qubit circuit. Actually, let me change this a bit. So I want to get the actual task. And then let's just see what happens. So first of all, we print out the actual task ID. And if you take a look at this, you can actually see what this is on the console. So if I take a look at tasks and I search with the task on, refresh, and this takes me to the task. This gives you a bunch of metadata about the execution details of the task. And then you can take a look at the storage location. You see that the results are stored in a JSON file, which you can download if you want. It's going to be some metadata in JSON format. So that's running a simple task on Amazon Braket. Let's see. So this is what we had. What if we want to run on actual quantum computer? I couldn't do it. I couldn't show you this right now because it's outside of the availability windows. But in principle, it's basically the same process. So you take the unique identifier we have over here, and then just replace that with a piece of hardware you want to run it on. So for IonQ, you can go to the console, look up the string, and then just initialize the AWS device with the string. That's basically the only difference between running on simulators and IonQ. Similarly, if you want to run on Rigetti's Aspen9 chip, you just copy and paste the identifier, initialize your AWS device, and there you go. That's it. Whoops. Previous. Yeah, so just to recap a bit, this is a slide we've seen before, but a typical Amazon Braket workflow will start out with you building your code on locally, so either on a managed notebook instance or on your local machine. So we have a fully managed development environment to help you do this, and then you test your code for the local simulator. Once you've done that, you can increase the number of qubits to, say, 20 or 25, which is where it starts to make sense, and then test it out using the circuit simulators that are on AWS. Once you've done that, then you can start running your code on actual quantum computers. And usually it just takes one or a few lines of code to switch between these three. We know it's not a linear process. You'll very likely just switch between all three stages as you go. And it's Amazon Braket's top priority to make sure that you have a consistent programming experience between these stages. Now that I've shown you this, let's get into a more involved example. So we'll take a look at variational algorithms. You've seen this earlier today already multiple times, I'm sure. And let me just briefly go over this again. So a variational circuit is, roughly speaking, it's just a quantum circuit with undetermined parameters that you can tweak. So this is, we can see how this goes with an analogy to classical machine learning. When you want to train a neural network, for example, you start out with a set of weights for the neurons, for the connections, and then you can use this to calculate the objective function or its derivatives, and that will get you a set of numbers. You use these results to update the weights, and then use that to calculate a new value for the objective function, and you update the weights, and so on, and you iterate until you're happy with the results or enough time has passed. It's the exact same thing for variational quantum computing. You start out with a quantum circuit with undetermined parameters. You use this to calculate some expectation value, so some cost function, or its derivatives, or its gradient. Use the gradient, for example, to update the variational parameters, and use that to calculate the gradient and objective function again, and so on until you're happy with the results. So we can do this on Braket through the Braket SDK directly. Actually, before that, let me talk a bit about a specific algorithm for this. So we'll take a look at QAOA to be precise. And roughly speaking, we want to encode the optimization problem is encoded in a cost Hamiltonian HC. And in QAOA, we want to just minimize the expectation of this cost Hamiltonian. So roughly speaking, the algorithm goes as follows. We pick a mixer Hamiltonian HM that is easy to implement. And we start out our state in an initial state. Usually this is the ground state of the mixer Hamiltonian. We evolve the quantum state under the cost of mixer Hamiltonians, alternatingly for varying periods of time under Schrödinger's equation. At the end, we measure the cost Hamiltonian's expectation, and we do this enough times to get a good enough expectation, and also its gradient if you're using a gradient-based approach. Finally, we use the cost and gradient to update the evolution times, and then we go through this process again and again iteratively until we're happy enough with the parameters we get, and we're happy enough with the final result, and then we try to extract the solution to the optimization problem. So you can code this directly in the Braket SDK. It's not too difficult. We have example notebooks to show you how to do this, but it's much easier if you just use PennyLane instead, because PennyLane is, as you know by now, it's a Python toolkit for precisely this purpose, for quantum differential programming. And there was a PennyLane talk earlier, so I won't go too much over these details, but it works on many platforms and many machine learning platforms and many backends just by switching. It's easy to switch between them. And there are also toolkits for machine learning, optimization, and chemistry. I'll get to batch circuit executions in a bit. Yeah, so we'll show this just by an example. We'll try to solve the maximum clique problem with PennyLane and on Amazon Braket. So maximum clique is just a problem of finding the largest set of vertices in the graph in which each vertex is connected to all the others. This example we have over here in this 6-vertex graph, the maximum clique is the 4 vertices down here, which are all connected to each other. So again, I'll switch back to the console. And this is just another example notebook over here. So PennyLane, graph optimization with QAOA. So yeah, the first thing we'll do is generate a random graph. And then this is pretty easy to do with PennyLane. So like most of the experience I say right now will have nothing to do with Braket. So you start out by feeding the graph to a PennyLane function, QAOA.maxClique, which will generate a good enough cost Hamiltonian and mixer Hamiltonian for you. This takes a few seconds, but over here you see we have a collection of Z terms for the cost Hamiltonian and a collection of X terms for the mixer Hamiltonian. Once you're done, you get these two Hamiltonians, the cost Hamiltonian, mixer Hamiltonian. You can define costs at the cost layer and mixer layer over here and combine them to make a QAOA layer. So this consists of an evolution of the cost Hamiltonian and an evolution of the mixer Hamiltonian once. For QAOA, you want to do this multiple times. So you can see this over here. I define my circuit by starting out in the initial state. This is just the equal superposition of the all qubits. And then I just apply this layer, the QAOA layer, 4 times. 4 and layers is 4 over here, using parameters I specify as part of the input. You've seen this before. And then initialize the parameters, define the device. Over here, we use the Braket local simulator. And to see the documentation for that, it's easy. You just search for PennyLane.ai, you go to the home page, check the plugins. Over here, there's the Amazon Braket plugin. And this is the local Braket device, the local Braket simulator. So you can see how to use this device over here. So we can just go ahead and do this. Define the cost function based on the cost Hamiltonian. Again, there are functions in PennyLane to do this. Choose an optimizer. Again, documentation, you can just see what optimizers are available. The gradient descent is just, it's probably the most vanilla of the optimizers. The more sophisticated methods, such as AdaGrad, but this is what we'll stick with for now. And then you just step through the optimizer step by step. You see over here that we start out with initial cost, and it will gradually decrease as you go on. This is not necessarily the case. It can jump back and forth, and you might need to tune the step sizes a bit, but this gives you the general idea. I won't wait for this to finish, but once you're done, you can try to measure multiple times the final state you get to get the most probable string. And when you convert the most probable string back to a graph, you see that this gets you the maximum clique indeed on this small example. Okay, let me switch back to the slides for a bit. Yeah, so this is what we had. Over here, we use the Braket local simulator by defining QML.device, Braket.local.qubit. If you want to use a managed simulator instead, it's pretty similar. You just use Braket.aws.qubit. You can, again, check the documentation. And to specify the device on, we've seen this before, specify an S3 folder, and it's the exact same thing that we've seen before. So that's the only difference. Now, one downside of training, actually before this, you can also run on QPUs. So if you want to run on Rigetti, for example, you just take the on for Rigetti and then replace it. That's basically the only difference. You do have to watch out that the circuit you want to run actually fits on the quantum computer itself. But other than that, there's not much difference. Okay, one problem with training variational circuits is that it can involve many circuit evaluations. So when you calculate a gradient based on, say, the parameter shift rule or finite differences, usually it takes a number of circuit evaluations, and that's roughly twice the number of parameterized gates in the circuit. And for these variational-based methods, oftentimes you'll have a circuit that has hundreds or thousands of parameterized gates. And so with gradient-based methods, each iteration you want to evaluate, say, one gradient, and that corresponds to hundreds or thousands of circuit evaluations. And so each gradient evaluation can take, say, an hour. And so training time really stacks up when you want to train for many iterations. Fortunately, there is a saving grace here. And that is that for each gradient evaluation, the circuits you want to evaluate are normally independent of each other. So the parameters in one doesn't depend on the results of another for when evaluating just one gradient. So that's why we enabled the parallelization of workloads on Amazon Braket simulators. If you want to evaluate one gradient, you can just send a batch of circuits you want to evaluate, and Amazon Braket will do this in parallel on a managed simulator. And it's pretty easy to do in Amazon Braket itself, but it's almost automatic if you do it in PennyLane. So PennyLane is small enough that when you run gradient evaluation and you specify the right flags, when it feeds it to Amazon Braket, it will automatically do the parallelization for you, and you don't have to worry about anything under the hood. So over here, we have this example on SV1. Right now, everything is done in serial, so it evaluates one circuit after the other. if you want to do this in parallel, all you need to do is take the definition of this device and add parallel equals true. Just add this keyword. That's the only difference. Once you've done this, it will send the circuits to the SV1 managed simulator in parallel. There are a few other things you can tweak. For example, how many circuits you want to execute in parallel at the same time, but that's the basic idea. And this really does give a big performance difference. Over here, I'm showing you the performances on 20 qubits between comparing between the penny lane local simulator default.qubit and SV1, the SV1 managed simulator executed in parallel. So already at 60 parameters, you see that you can get, say, a 10x runtime difference. And for realistically workloads with hundreds of parameters, the difference only gets bigger. So this is a good advantage of the Amazon backend managed simulator for variational quantum workloads. Okay, in summary, I'm just going to go back to the 3 pillars we had earlier: build, test, and run. So to help you build your code, you can get started quickly with a fully managed development environment. All you need is an AWS account and a web browser, or you can install the software locally if you'd like. You can prototype solutions with the local simulator, and if you want to build variational algorithms, you can also just use PennyLane, which comes pre-installed in the environment. Once you've done building your code and you want to test it, you can use our fully managed simulators to test and fine-tune your algorithm. You don't have to worry about any of the infrastructure heavy lifting behind the scenes. And for larger circuits with specialized structure, you can use our TN1 simulator to test them out. Finally, if you want to, if your workload involves parallel execution of circuits, and variational quantum algorithms are a very good example of this, then running them on SV1 allows you to get significant speedups. Once you're done with all of this, you want to run them on quantum computers, and Amazon Braket provides you with secure and on-demand access to a few quantum computers, and you can expect that the selection will expand in the future. Again, you'll switch back and forth between these 3 pillars, and I hope I've convinced you by now that it's Amazon Braket's priority to make sure the experience between these 3 are as consistent as possible. Let me just end on this slide of links. I've just given a link to documentation to Amazon Braket and PennyLane. The example notebooks I demonstrated today, they're available on the online notebook instances in your AWS account, but they also are just in this GitHub repo that you can take a look at. And for more details on PennyLane, PennyLane has an absolutely amazing website with many examples that I highly recommend you take a look at as well. Thank you.
Thank you, Cedric. Oh, I got some echo. Okay, I think it's okay. Are people getting echo? Getting an echo. Okay.
Maybe no, it's fine. Thank you so much, Cedric, for the great talk. It was actually my first time seeing, like the integration of PennyLane and Braket in the wild live. I hadn't seen actual snippets of code, so for me at least, it was really great to be able to see this. We have a few questions from the chat, so I'm just going to pass it over to you. One very straightforward question is, can you elaborate more on the pricing model used by Braket? And you can unmute yourself, Cedric. Yeah, you're still muted. We had the echo, so you're unmuted, but if you could unmute yourself.
Sorry for bringing this back up again, but let's see. So that's a great question, which I probably should have covered in a bit more detail, but this is pretty easy to find if you just Google Amazon Braket pricing, and this will take you to the page, Amazon Braket pricing. So there are a few things that are charged. So the managed notebook, it's based on SageMaker, and you can visit the SageMaker pricing page. For the simulators, local simulators, of course, free because as you know, everything is run locally. The local simulator, sorry, the managed simulators are charged per minute at the rates shown over here, and that's it. So it's based only on execution time, and it also belongs to AWS free tier. So you get an hour of free executions on these two simulators. For quantum computers, we charge mostly based on a per shot basis, and this is essentially this is essentially based on discussions with the quantum hardware providers, and we also think that this provides the most value to our customers because this is really the pricing model that makes sense. I think this corresponds to how many times they need to run a quantum computer, and this is very much in line with our on-demand philosophy.
Excellent, thank you. Another question from chat is, so Braket has access to simulators and devices. Can you comment on the ability of the simulators to also take noise into account and the imperfections, and how they can be adapted to the specific hardware backends?
Mm-hmm. That is a great question. Right now, our simulators don't support the simulation of noise just yet, but we are always looking for ways to improve the simulations. And so that is great feedback. That's certainly something we'll take into account when improving our simulators.
Awesome, thank you. So I think that covers most of the main questions from the chat. Now we can maybe transition a little bit to the more informal conversations that we like to have at the end of these talks, if you don't mind. So I don't know if you were there for Nathan's talk this morning, but there were some Dungeons and Dragons aficionados in the audience that spotted some D&D books that he had in the background. So I've heard that you like to also be a dungeon master. Maybe you can share some of that experience and that part of your hobby with the audience.
Sure. Yeah. So I really love tabletop role-playing games. I actually haven't played D&D that much. I play mostly the Pathfinder role-playing game, and that started out with a group we had back in MIT, and so we've just been keeping with touch mostly through Google Meets nowadays, and it's a group that is spanning continents because people are just scattered all over the place right now, and somehow we've kept this group going. And what can I say? I'm the main DM for this group right now, and I don't know, it's pretty fun coming up with stories and taking my group members into these stories, and it's a good break from life. Sometimes life it doesn't have the best answers to everything, and not everything is in a black and white morality. But I feel like these Dungeons and Dragons games it helps you to figure out what your ideal self is, like what you would like to be. It just frees you a bit from the constraints of real life, and maybe gives you a chance to explore what you would like to be.
I love that. It's great. For some reason, I haven't myself played this role-playing. I've done a lot of video games that are RPGs, and I love reading like fantasy, and I love like that, what you just mentioned, right? That ability to kind of loosen some of the constraints of real life and just explore. I think it's something that shows up in my science as well. I just like to push boundaries and try out new ideas. So that was great. Thank you for sharing it.
So I also heard that you like playing table tennis. Is that correct?
Yeah.
So do I.
Oh, great.
Right? Yeah. Can you elaborate a bit more, and we can have a table tennis chat?
Table tennis chat? I'm not sure I have that much to share. Like, I grew up back in Taiwan, and so I think ping pong was just one of the things that a lot of people played there, and like that's just how I got into it. And this is basically continued. For that matter, I also like badminton. These seem to be stereotypically Asian sports for some reason, but I am not sure I have any interesting stories to tell you, but just I've been a fan since I was little.
I can ask you some questions. I love table tennis. This is my favorite sport. I've tried many sports in my life, and table tennis is my absolute favorite. For those of you that don't know this, we have a table at Xanadu. Of course, during COVID, we haven't been able to make much use of it. We have tournaments. I've won both of them, by the way. And we have technically actually a lot of fun. So something that I want to do now, which we did in the first talk, is to do a lightning round of questions. So I'm going to ask you a few questions, and I'm going to start with some table tennis questions.
Right?
Yeah. So what is your strongest shot? Is it the forehand? Or is it backhand?
Definitely forehand.
Okay, and a lot of people don't realize the role that spin plays in this sport, right?
Yes.
And so I like having fun showing them all the different spins, right? So you can have topspin, you can have backspin, you can even have side spin. Which is your favorite spin to use against opponents?
Topspin, mainly because I'm pretty bad at the other spins.
Okay. My favorite, by the way, is just to serve with a lot of side spin and then just look at people's faces when the ball just goes completely to one side and they cannot explain it.
Yeah. So when I say I love table tennis, I did not say that I was good at table tennis. So it sounds like you'd probably destroy me if I enter one of your tournaments.
It's all about having fun, right?
Yep.
And are you more of a looper? Do you like to loop or do you prefer to block?
I'm not sure I have a preference there. Probably block. I'm not super sure.
All right, and then the final one. Do you have a favorite table tennis player?
No, like I'll admit that I watch table tennis much less than I actually play it.
Okay, fantastic. So that's the questions that I had. What I would like to do now is something that Paul did in one of the previous talks, which we're going to play. Do you know what Mad Libs is?
Oh man, Mad Libs, sure.
Yeah, so we're going to do a quantum version of Mad Libs, right? And so the idea here is we're going to do a Mad Libs for the intro of a startup's website, right? So I'm going to ask you to give me some words, and we're going to fill in the blanks and then read it afterwards, right? And everyone watching, I encourage you to also contribute with your own ideas, right? You can play along and then kind of replace as I do this. So I would like you, Cedric, to give me a synonym for money. Something else you use to refer to money.
I would say cash, but that seems too common. Let's say Benjamins.
Oh, wow. Okay. That's a good one. Okay, and can you give me the name of a fruit? A fruit.
Let's see. What's that stinky fruit in Southeast Asia called again? Let's go with that one. I forgot what it's called.
Durian. It's durian.
It's
Durian. Yeah, not everyone will agree with you. Some people really love it. That was a big thing in Singapore. I spent a couple of years there. Okay, you should be an expert at this. Can you give me the name of some fictional place?
Fictional place. Yes. Let's go with the Shire.
The Shire. All right. That's a good one. All right. And can you name something fast? Something that's just really fast.
Race car.
Okay. Oh, this is shaping really well. And what about a subject that children would study at school?
Quantum computing.
Oh, really? Okay.
I mean, there's a book for quantum computing for babies, so I guess.
Good point. Let's use it. What about a species of bird?
Ostrich.
Whoa! Oh, you're good at this, aren't you? And what about a job that requires wearing a uniform?
Soldier.
All right. And the name of an expensive hobby. So a hobby that should be really expensive.
Art collection.
Sorry, what?
Art collection.
Art collection. Okay. Okay, almost there. Now, how about something from a kid's birthday party? Something you would find at a kid's birthday party.
Clowns.
Oh, this is gonna be good. What about a word that you might overhear at a supermarket? Something people might say in a supermarket. Just a word.
Mommy.
Oh, this is gonna be really good. I think I want to share it in the chat at the end. What about an unusual house pet? So a house pet that's not a typical one.
Sorry, did you say a name of a show?
No, an unusual, so like a very rare, exotic house pet. So like an animal you would have at home as a pet, but that's very unusual.
Anaconda.
Wow. What about a famous celebrity?
Famous celebrity.
Yeah.
LeBron James.
Oh, good one. Okay, 2 more left, and then we'll read it out loud. What about an overhyped technology that's not quantum computing?
You took my words away from there, but let's see. A Bitcoin.
All right.
This is gonna be controversial, isn't it?
Nah, it's not gonna be. And finally, what's a type of food that rich people would eat?
Gold. I think I've heard of people eating gold-plated food, so let's go with that.
All right. So we ready? That's the end of the Mad Libs. So I'm just gonna read this. This is the introduction, the main page of the website of our new startup. Welcome to Quantum Benjamins Corporation. We build quantum computers using the quantum properties of durians. It's a spin-off of the University of the Shire's famous startup hub, Rayscar Labs. Actually sounds pretty good. Our world-class team has advanced degrees in quantum computing, ostrich management, soldier studies, and art collection. We are backed by some of the world's best investors, including Clowns Ventures, the Mummy Fund, Anaconda Investments, and LeBron James Capital. You might have, actually, some investments. Sign up now to join the beta test for a Bitcoin-backed quantum computing operating system, codenamed QGold. And that's it. Let me share it very quickly with the chat so everyone can have a look at it. Hopefully.
Yeah.
There we go.
Back to quantum computing. But I feel that alarm bells immediately start going off.
Yeah, I think that was pretty good. Oh, I wasn't able to share everything, so let me do the second part. Cedric, anyway, that reaches the end of your talk. Thank you so much for the great presentation and for indulging us in this activity. I think we all learned a lot. And have a great day.
Yeah, thank you, Juan. Thank you for hosting.
My pleasure.